Okay, when I first started filming for this video, I wanted to try isolating potassium osmate. Didn't really go as planned, but some good things came out of the experience. And a mystery that has been plaguing me for some time has finally come to light. And I've got it pretty well figured out.
Two sodium osmate solutions were prepared. The first one I prepared by dissolving osmium metal in bleach to which I had added a minimal amount of sodium hydroxide. To this solution, I added potassium hydroxide, and the color of the solution darkened. There was no precipitate. Once a significant quantity of potassium hydroxide had been added, the final solution looked no different from regular sodium osmate. The second solution was prepared by dissolving osmium metal in bleach to which I had added a significant quantity of sodium hydroxide. This was to concentrate the solution. I also dissolved more osmium in this solution as well. Here you can see the two solutions compared side by side. On the left is the sodium osmate solution, and on the right is a solution containing some sodium osmate and some potassium osmate.
The issue here is that sodium and potassium osmates don't really exist separately in solution. It's just a bunch of osmate anions and a bunch of sodium and potassium cations, just floating around in a mesh in solution. And what I'm trying to do is I'm trying to isolate potassium osmate by double decomposition due to its lower solubility.
Another issue was that this sodium osmate solution wasn't concentrated enough. I had previously found a patent describing the production process of potassium osmate, and it cites that it can be made by double decomposition with concentrated sodium osmate. Nevertheless, I soldiered on with what I had. Adding potassium hydroxide to this sodium osmate solution merely darkened it. However, I experienced a false sense of promise when a thick, dark layer began to form at the bottom of the vial. I stuck it in the freezer for a bit, but this was to no avail, as the water was freezing and no solid precipitate had formed. Under a flashlight, it became clear that this darker layer was simply a denser, more concentrated layer.
That's a problem.
And not a precipitate. Well, mission failed. Time to recover the osmium.
Now, this is the part that made me nervous at first, because although I've successfully precipitated osmium dioxide from osmate solutions many times in the past, lately I've been having trouble with it. Instead, I've been getting a clear solution of hexavalent osmium in which the dioxide seems to just dissolve in. And it hasn't been making any sense, and I haven't been able to figure out what's going on until now.
To reduce the osmate solution, alcohol needs to be added. This time around, I thought I'd use vodka like I used to in the past. Now, it should be noted that osmate solutions do not turn pink or purple unless they've been reduced from their corresponding perosmates using alcohol. So simply adding alcohol to an osmate solution will not result in that pink or purple color. Next, I start adding dilute hydrochloric acid to precipitate osmium dioxide. But once again,
oh, you son of a bitch.
not to be defeated, I added potassium hydroxide to convert the solution back to potassium osmate. You can see potassium osmate forming before it dissolves in solution. What you're seeing in the upper layer is the potassium osmate being swirled up. It mixes with a more acidic layer of the solution and is reduced back to osmium dioxide. This dioxide then continues dissolving in this upper layer. This process continues until the pH of the whole solution becomes alkaline. Now that I've reacquired potassium osmate, I try again, but this time with concentrated hydrochloric acid. I use an excess of it in hopes of getting chloroosmic acid. At last, I have succeeded in reducing the osmium to the +4 oxidation state.
And from here, I can then make this alkaline, and it will reduce to osmium dioxide whether it likes it or not. You stinking cocksucker.
However, in an act of complete and utter disrespect, the osmium reoxidized to the +6 oxidation state overnight, and I was left sorely wishing I hadn't waited to make it alkaline. Nevertheless, I added more potassium hydroxide and made it alkaline once more. The same process I described before can be seen again. It actually kind of looks like the debris cloud of a tornado. This time, the osmate solution did turn purple, leaving me wondering if the osmium ever went to the +8 oxidation state or not. I don't think it did. Crystals of potassium chloride can be seen at the bottom of the vial. They precipitated out because they have a much lower solubility in water than sodium chloride. So ultimately, I decided to do what I normally do when these situations happen. I add ammonium chloride to reduce the osmate to osmium oxydiamine hydroxide. Now I just have to wait overnight for the oxydiamine hydroxide to precipitate out.
Now, I had to figure out what to do with the other solution, because I haven't done anything else with it yet, and I had to sit and try and figure out what to do about it because I am so afraid of screwing it up again. But it doesn't make sense. I've done this so many other times before and it's always worked. I've always gotten osmium dioxide out of solution. I don't know what I'm doing wrong now. What am I doing wrong? What am I doing differently now that I wasn't doing then? And then I figured it out.
I forgot to remove the bleach. So I decided to neutralize the bleach with about 10% hydrogen peroxide. I add this directly to the sodium potassium osmate solution, and this will of course oxidize some of it to sodium potassium perosmate. Now remember, so long as the pH is high enough, around 14, perosmate solutions will not give off volatile osmium tetroxide. I continue adding hydrogen peroxide until the color of the solution begins to lighten. This will tell me that perosmates are forming. Using my own judgment, I decide that the solution is ready, and I begin cautiously adding 95% ethanol to the solution. Once the osmium is fully reduced back to the +6 oxidation state, I gazed upon the two solutions, thinking to myself, this is the kind of thing you get to see when you work with osmium. Finally, I begin adding dilute hydrochloric acid to the solution. From here, it's business as usual, and everything happened normally. No clear solutions, no redissolving dioxide, just osmium dioxide coming out of solution, and it's beautiful. Plus, I've been wanting some more osmium dioxide because I want to make ammonium hexachloroosmate again.
Yes. You, bleach. You. You. You.
After centrifuging the osmium dioxide out of solution, I was very disappointed to see that I got a very low yield. However, I discovered that the leftover solution contained mixed oxidation states of osmium, mainly +4 and +6. This solution contained hexachloroosmate, and upon adding potassium hydroxide, a much larger yield of osmium dioxide fell out. After adding more potassium hydroxide, the solution became alkaline, and the purple color of the osmate returned. However, this began to decompose as well into more osmium dioxide.
Did a good job this time.
Alright, so I've got quite a bit of osmium dioxide there, and I still have to add all of that osmium dioxide to this stuff. And honestly, it looks like the solution is still decomposing. It's getting really dark. Now, the osmium oxydiamine hydroxide has already begun precipitating out. And this time, I'm not going to make the same mistake that I did over here. I'm going to allow the oxydiamine hydroxide to coat the sides of the glass, and I'm going to wait a long time for it to get a nice thick coating, and I am going to remove the solution before scraping the coating off. Otherwise, you get just a thick sludge like this that you have to, well, deal with. And I have some more oxydiamine hydroxide here. I'm planning on getting all of this and mixing all of it with hot concentrated sodium hydroxide to convert it to osmium dioxide. Now, at this point, I'm sure you're all expecting me to explain what happens when you acidify an alcoholic osmate solution without taking the bleach out first. Well, I have some ideas, but no certainties. Clearly, the bleach is keeping the osmium in the +6 oxidation state, or at least making it difficult to reduce. And if it does reduce, it's liable to reoxidize. This was seen earlier when osmium dioxide was quite visibly dissolving in this clear solution, and when my chloroosmic acid frustratingly reoxidized to the +6 oxidation state. It's also possible that the interaction of alcohol and bleach is catalyzed by osmium and some kind of chlorinated solvent forms. I'm not sure it's chloroform because I've never seen any like dense solution hanging out at the bottom of the vials, like ever. It's also possible that osmium complexes with it and forms something completely different that's sort of clear colored. About potassium osmate, yeah, that's a damn shame. But I also sent poor man's chemist about 4.3 grams of osmium, and he has yet to do anything about it. And this is the second time I'm mentioning it in one of my videos. But since it's safe to assume that he's never going to get around to it ever, not ever, I am actually considering at this point investing in a vacuum desiccator and a vacuum pump to go along with it. And I'll probably have to invest in some kind of kit to dissolve osmium in a melt of hydroxide and nitrate. And then after that, just vacuum desiccate it and hope that the potassium osmate doesn't decompose and coat the entire vacuum desiccator in osmium dioxide, because that would suck.